Right, hi everyone. Thanks for joining the fourth episode of our Power Hour series, where we're going to be covering electrical protection, fault levels, coordination, and arc flash studies, and hopefully try and explain them in a practical way. For those that don't know me, I'm Dan Henderson. I'm the Global Head of Electrical Safety and Partnerships here at Scanware. I'm a chartered electrical engineer based in the UK with a varied background across military, defence, renewables, civil aerospace, and utilities around electrical safety, and particularly high voltage and management of HV systems. I'm joined today by Jeremy Gadd from Corval Engineering, who's going to be supporting our Power Hour as our SME. I'll pass you over. And Jeremy, if you can tell us a bit about your company and yourself.
Thanks, Dan. We're Corval Engineering. We're a UK-based electrical engineering design company based in Billingham, which is in the northeast of England, not far from Newcastle, above Manchester, on the coast of the North Sea. The company has been in this format for the last 8 years. We have a long history of working with heavy industry clients, typically chemical, steel, pharmaceuticals, and we've done that for some time now. We provide support electrical engineering based design projects, studies, the likes of these types of studies that we're going to go into now. And we've got a good, strong set of guys who are competent and capable and have a lot of experience in performing both protection and arc flash studies. Types of industries, it's the straightforward, the usual stuff: manufacturing, pharmaceutical, utilities, oil and gas, aerospace, and more recently defence. As far as my history goes, I go back right the way back to the 1980s, where I served an apprenticeship with what was then ICI Chemicals and Polymers, then promoted up through the ranks to electrical control instrument asset engineer, where I was responsible for reliability, longevity, performance, output from the electrical engineering perspective. Shortly after that, I left the company and became an engineering manager at another tier Colma site. Colma is a set of regulations that cover industries in the UK. Stands for the Control of Major Accident Hazards, and this is where companies operating within the law can have an impact on societal risk, and that's the public in general. So a lot of very stringent rules to get through. After there, I went and joined the head of department for a consultancy company and later became managing director for that company. In 2018, I set up Corval Engineering, and I've been the managing director plus consultancy since then. That's a quick plotted history of my career.
Brilliant. Good to have you with us today, Jeremy.
Thanks.
So a bit of housekeeping. You will receive the slides after the webinar via email if you're registered for the event. You will get a recording sent also. Please use the post-webinar survey. Let us know how we did. Anything that we want to do differently, or future topics. We'll be looking at presenting those on the next one for what's going to come in 2026. Please make use of the Q&A. Enter any questions, and hopefully we'll have time at the end to get through some of those. Yeah. And if you want to be registered for future events, let us know in the chat. Yeah, thank you. So just I suppose a quick recap for people that haven't attended. You can still get access to the recordings of these and the slides. So we started off because electrical safety and management of electrical networks is such a big area, such a wide field. We've tried to use this as a bit of a journey. That's why we've done it as a series. So break it down into bite-sized chunks that we can work through together. For people that are either responsible for managing electrical networks, certain parts of electrical safety, or health and safety, just to get an understanding around that. So we looked at initial electrical asset management, or building your asset lists, what's important on there, what's not, how you can use that to then build your maintenance plans, look at operational restrictions, and do your business impact assessments. We then focus that down into your typical electrical maintenance in a prescriptive way, so based on O&M guidelines and any guidance such as NFPA 70B as an example. And then we've focused that down further. We had a collaborative session last time with VPS, looking at understanding oil sample analysis, those results, the types of things that indicates in terms of asset health and electrical safety impacts, and some mitigation factors in there. So today we're working with Coval Engineering and looking to try and talk through understanding your protection studies, how that the outputs of that in terms of time current curves and your electrical fault levels and subsequent incident energy in terms of arc flash. And then to finish off the year, we're going to get some industry professionals together from a couple of different industries, work through a real life incident and do a root cause analysis together with you guys as attendees to try and work through what the root cause was of the incident. So it should be a good series up until the end of the year. So the learning objectives of today: understand the importance of protection, coordination, and fault level studies, interpret and apply the study outputs, including how to interpret the time current curves, connect protection and fault level studies to arc flash and NFPA 70 compliance, and understand incident energy and any mitigation strategies as well that link to that. So just to kind of recap, but take us into the where we're starting here. Why do these studies matter? So legislation is a key driver, as well as trying to do the right thing and keep people safe. As we've covered in the past, it doesn't matter what industry you're from, whether you're heavy industry, heavy manufacturing, data centers, renewables, whatever your industry, whether you're whatever your geographical location, there's always responsibilities for health and safety in the workplace. And typically the person with the most responsibility, in our example here on our site, our general manager, has the most responsibility and is responsible for the health, safety, and welfare of all persons on this site. Obviously, they can't be everywhere. They're running a business, and they typically aren't experts in specific technical disciplines, such as electrical, which is our discipline here, and it's a high-risk, high-consequence system. So that person will typically appoint someone to have responsibilities to make sure those high-risk, high-consequence systems are safe on their behalf, to make sure that they stay compliant, and that they ensure the health, safety, and welfare of the people on the site. So in our example, we've got Eddy Electrical as our responsible person, but it could be an energy marshal, a licensed electrical worker, whatever the terminology is in your geographical location. So the bits that we're going to look at in terms of this responsibility is protection, coordination, and arc flash surveys. So one of the things that we want to just look at of why we do it in terms of guidance and legislation. So we're looking at the differences between prescriptive and risk assessment approach. So for geographically, there are differences. So in the US, we've got standards shown there. So NFPA 70E, which is the standard for electrical safety in the workplace, and 70B, which is the recommended practice for electrical equipment maintenance. So those documents are very prescriptive and they use mandatory terms. So when I'm saying mandatory terms, they are terms with no justification or qualification. So they are shall, must, terms like that, which mean you have to do them. And because they're prescriptive in a way that they say you shall do this, you shall do it at frequencies of, so typically 5 years or any significant changes. So they are very prescriptive in their nature to say how you will comply. And if you do comply, to a minimum, you'll keep people safe. Whereas other places, UK-based legislation and others, there are a lot that it doesn't specifically tell you in terms of fault levels and arc flash, what you shall or what you must do. It uses terms such as shall where reasonably practicable, which is based on risk assessment. So it's the risk balanced up against the time, cost, and effort of mitigating that risk. Risk being the probability of the event against the consequences of the event as well. So when we're looking at that risk assessment approach, the things that the hazards that we're trying to mitigate against are electric shock, electric burns, fires of electrical origin, electric arcing, which is obviously the arc flash element that we're talking about, and explosions initiated or caused by electricity. So if we're looking at them as hazards, is it in the UK as an example, but it's similar in other geographical locations outside of the US. When we're looking at that, when we're looking at approach for risk assessment, we have got legislation in place which is mandatory, but the terminology is direct, such as the Health and Safety at Work Act, which is legislation. And what it says in there is that the employers shall ensure the health, safety, and welfare of the employees. It doesn't tell you how to do that, it just says that you have to do it. So it is direct, it is mandatory, but it's not prescriptive, as in the same way that NFPA 70 is written. Then likewise, we've got regulations, which are also legal documents, and in there it'll get reference things like the strength and capability of electrical equipment, the means for protecting against excess current, and ensuring that your operational networks don't give rise to danger. It doesn't tell you how to do those, just tells you that you need to make sure that they don't do that and that they are safe to operate and maintain. And then finally, when we come to risk assessment, again, most places in the world has a similar terminology around employers making sure they've got suitable and sufficient risk assessments for all known hazards in the workplace. So again, there's nothing directly in other places saying that you have to do these specifically for arc flash and fault levels, but ultimately, when we're looking at hazards and all known hazards, one hazard is the catastrophic failure of switchgear or an arc flash. But we need to know the severity, because in order to do a risk assessment, we need to know the likelihood and the severity. And we can't know the severity without modeling that data and knowing what that incident energy level is. So these are some control measures around that. So managing the likelihood would typically be run through safe systems of work, the competence of the operatives and the equipment itself. And then trying to manage the factors that influence the severity is the energy levels, the available fault current, the disconnection times on our protection, and the location of the operatives. And then finally, just some additional things of why these studies do matter as well. There's some best practice based on IEEE and IEC standards, which again may be the basis of your direction where you are geographically based in the world. Operational reliability. So from a loss prevention and risk management perspective, we also want to make sure that we've got suitable resilience and know that that network's going to operate as it needs to, either in the event of a fault or in normal operations. Which also links from a loss prevention and risk management perspective. A lot of insurance companies in terms of this are based on FM Global standards. In FM Global, there's a strong direction around arc flash mitigation of electrical faults because of the significant downtime that's caused to the businesses, as well as a corporate requirement. You might have your own standard that insists that you do these studies as part of your loss prevention, risk management, and or safety. And then again, with organic growth of your business, any increase in capacity on your network is why you need to look at these as well. So whilst we just looked at why we do it, just want to get a quick understanding from the people on the call. So what's the main driver behind your network studies? Is it to comply? Is it for the safety of persons? Network reliability? Does the insurance demand that you do it? Do you not do these? You might have all of them. I suppose it's just good to get an understanding of why you do these in your locality.
So the poll is up now. Just a reminder, it is multiple choice, and I'll give it another 10 seconds.
Thanks, Ben.
5. Right, I'll stop it now and share the results.
Good to see safety of persons being top. And compliance is, I mean, sometimes they go hand in hand. I suppose that's the good thing with a multi-choice. Just sometimes you do get, some people being very compliance driven. So we do to comply being the main one. Good to see company policies as well. Let's see how long it takes to go to the next slide now, Ben.
Technology.
Oh, it's always on these polls. I don't know why. There's got to be a setting somewhere. Okay, I'll hand you over to Jeremy now.
Thank you, Dan. Great introduction. Okay, so we're going to discuss hazards and consequences, and we're going to talk about 3 topics. Those 3 topics are protection coordination, fault levels, and arc flash, and discuss the hazards and consequences of each of those. So the distribution system, when we're talking about coordination, I've put together a little chart of a basic distribution system. So you have a utility infeed at the top that then sub-distributes down to further distribution, and again sub-distributes down to further distribution, and finally down to single boards where we may have motors, MCCs, or whatever loads you've got at the bottom of it. Within coordinated distribution systems, what tends to happen is if a fault occurs at the bottom of that distribution system, that will propagate its way up through its distribution above it, through any main panels that are above that and keep on going all the way up through the other distribution until it finally reaches the utility incomer, DNO incomer. And what then happens is that piece of protection will then operate, and that results in the whole of the site being depowered. That's a pretty significant event, and we've put this in just to illustrate or exaggerate even how an uncoordinated distribution system could operate with a fault right at the bottom of it. You know, full site power loss with miscoordinated systems, you may get some of the distribution going off. It may stop at the first or second main boards. It's highly likely that you're going to get equipment damage because the piece of equipment at the end where it's subject to the fault will only have its power put when the in-feed protection, which is operating at pretty high levels, finally recognizes a fault. Increased chances of injury if people are around or nearby when that occurs. You know, it can be a blast, it could be a small explosion. And then probably one of the main things about this as well is it's very, very difficult to determine where that fault originally initiated from. Similarly with miscoordination, you get very much similar effects as a result of miscoordinated distribution systems. The only benefit could be that, you know, you may cut off at the first board rather than all the way up to the top to your main in-feed. That's just to give you an indication of what protection coordination is trying to achieve. Is trying to avoid that whole fault propagating all the way through to your main in-feed.
Yeah, so I suppose just to give some context to that on a single line or a one line diagram. So taking that existing model, if we had a fault down here, we would expect the protection to coordinate in such a way that if it's a fault down here, we'd expect this this switch to operate first. If it then got onto the network, we'd then expect this circuit breaker to trip. If it then didn't operate the protection there, we'd expect this one to go third, and then finally the in-feed. So that's how the protection should coordinate. And obviously, to reiterate what Jeremy said, you could have equipment fed off this board, which is either safety critical, business critical, and rather than just losing this non-critical distribution board, you could end up with a miscoordinated or uncoordinated system. You could lose a lot, and some things could propagate into a safety related or a business impact scenario.
And typically with fault levels, and the picture that's shown there shows the after effects of a pretty much an explosion, after explosion. High fault levels, you know, can lead to physical damage to the distribution system when you get that much energy going through, you know, pieces of equipment. The thermal energy and the stress that's created as a result of it, in essence, tears the place apart. Equally, high fault levels can have a big impact on getting good discrimination with your protection systems as well. And finally, with that as well, you do get higher incident energy levels, which we'll come on to later. You're overlooking equipment design ratings. You know, if you've got short circuit withstand ratings of equipment that you know about, and your fault levels are exceeding them, you know, you basically set yourself up for a fail at some point. And finally, the other thing that contributes to higher fault levels is just the organic growth of a distribution system, whether it's through small minor projects or whether it's through major expansion. You know, you could be putting more reactive equipment on, selective motors and generators. They all end up contributing to your fault levels as well. So you can quite easily increase without really anybody keeping the finger on it. This is why the likes of these studies that, you know, the fault level for protection for Arc Flash are essential to be done on a routine basis. So again, retaining with capacity consequences for Arc Flash. So if you've not got an Arc Flash risk assessment in place, the likelihood doesn't alter. You know, that event may still happen. There's the potential for serious injuries when operating switchgear. There's the potential for permanent equipment damage as a result of an Arc Flash incident. That's primarily known as arc blast. And you're unable to determine the necessary PPE for any sort of switching operation that staff should be wearing. And equally, you're not compliant with best practice. Arc Flash assessments are now, you know, they're on the rise now because people do recognise the importance of them. If you have had your risk assessment put in place, but you've not taken care of any mitigation, you've identified that you've got high incident energy levels, not applying mitigation. Basically, the main problem here is you've got known hazards, high incident energy, and basically you then need to take even more onerous steps to prevent injury or harm to your staff when you then go and operate pieces of switchgear that may present high incident energy levels. So the whole thing is all one to ensure that the hazard and the consequences are managed. Once you know about it, you really do need to do something to reduce it. So this is our example distribution system that we're going to use, and Dan's mentioned it earlier. It's a simple system. It's got an 11,000 volt in feed, goes onto a main 11 kV board that supplies 2 transformers. We then come further down, we've got 2 LV boards, LV board A, LV board B, and they've got a bus coupler sat in between them. And then we have some sub-distribution, a couple of distribution boards and MCCs at the bottom of that. Really, really simple stuff. It's just to illustrate our coordination studies and our Arc Flash as we come on to it. So the main start of any particular study, in this case, we've started with protection coordination, is data collection. There are 2 ways of getting that data, and one is provided by the client. The other is via a site survey that's conducted by the people who are going to produce your study. Just a point to note, if you're leaving it to your supplier to conduct that site survey, that can probably be anywhere near 25% of the cost of the whole study. So because it's a really onerous task to go and do. And the reason why it's so onerous is because the amount of information you need to collect. And this is typically broken down into 3 sections. One, it's the equipment. So you can see around there, transformer data plates. We need to take that information. You've got panel bars that'll have the similar information that we need to model those in a software simulation. You've got switchgear rating plates that we need to get their information from as well. You've got then generators, any renewables that you've got, whether these are PVs or whether these are wind farms. We need to know what protection devices you've got in place along with their CT ratios. We need to know cable details as well. For the data, so I've used the word DNO. This is just utility provider. Each of those in the UK, we use the words DNO, distribution network operator. It's basically a utility provider. We need to know what in-feed details that you've got going to your site or your facility. We need to know what fault levels you've got, and we need to know your existing protection settings. And finally, for documentation, single line diagrams, 1-line diagrams. We need whether you've got previous reports, any equipment specifications or design data that you've got, and ideally cable schedules that will give us the size and length of cables, along with routing maps as well. So there's a considerable amount of information that we need just to actually create the model before we even start any type of study.
Yes, I suppose just to add on that, we know how much, like, there's a lot of information there, and obviously that's just a 1 line underneath that. It is all that information. There's quite a lot to supply. So if we were going to do a study on your site tomorrow, how much of this information that we need would you have available? Just do a quick poll, just to, because I know how difficult this is. From it'd just be interesting to see the people on the call what they would typically have.
We've received nearly 50% participation, so I'll just give it another couple of seconds.
Perfect.
3, 2, 1. We're at 65 plus now, so I'll share it in there.
Yeah, that's probably where I'd expect it. Well done for the ones that have got all of it.
Yeah, exactly.
Yeah, some of it's probably the majority, because most of the time things aren't kept up to date. That's typically what we see all over. It's not you're not alone. It's that's probably what I would have expected. So thanks for that.
Excellent.
Just gotta see how long it takes now, Ben. Could be so quick. Right, back to you, Jeremy.
Okay, so once we've collected all that data, we then start to give it a quick sanity check and reconciliation just to make sure there's no conflicting information in there. And from that, we then build the software model using the data provided. Just in terms of software model, there's numerous types of modeling software out there. We use SKM Power Tools. We found that to be the most flexible and useful, provides really good results and good reports. ETAP, IPSA, DigSile, and there'll be others out there as well. I'm not here to profess that anyone's better than the other. It's whatever you're used to. So once we've built that model, we then compile the software to make sure that it's producing the results that we expect. It's a second sanity check. You're all aware of all the data. If you put rubbish into a software model, you're going to get rubbish out. And once we've proven that the model's good and producing the right results, we're then ready to conduct the studies. So for protection coordination, what we start off with is typically the highest load on any given distribution board, and that's because the highest load is going to provide the highest current when it comes to tripping it. If we use low loads, you're going to overlook that and you're going to end up with spurious trips. Once we've selected that leg to check the coordination on, we then produce time current curves, TCCs, that incorporate the source of the supply all the way down to that load. And we're going to come onto these curves shortly. What we then do is visually check the curves and look for overlap or any clashing of those protective devices. So our first curve that we see from that, if I just explain this slide a bit, on the right-hand side, you'll see that that's a little cutting of the distribution system that we've used as an example. So all the way from your in-feed through your HV circuit breaker, your transformer, your LV circuit breaker, your main board, and your two loads beneath that. The middle drawing is that same distribution from the model that's taken from the model. So you'll have a lot more data on there now because we've got the likes of cable details, short circuit details, ratings of equipment, settings of equipment, CT ratios, and so on. So there's a lot more detail in the model. Anyway, to bring all that into the time current curve, which is shown on the left, just quickly to give you a bit of a background. So time current curves are produced on logarithmic plots because the size of the curves, if you use a linear chart, would be enormous. You couldn't fit them on the page. So the x-axis shows our current in amps ranging from 1 to 100,000 amps. So our y-axis shows our time in seconds, starting from 100 or 10 milliseconds all the way up to 1,000 seconds. And that just gives us the breadth that we need. So if we start to read our time current curve now, our TCC, I'll describe each of these curves that are on here. So we'll start with the blue one. The blue one is our LV board, which is our left-hand side incomer. And that's the piece of protective equipment that comes straight off the transformer. The second curve that comes in under there, which is the brown one, is our LV CB1, which is our main protective device that's protecting DBA1. The next curve that you'll see on there is the red one, and that's HVCB1, and that's our protective device that's protecting the in-feed into the transformer. And the final one that we'll use on here, which is the purple one, that's slope, that's the LVFS1, which is a fuse, which is shown again on our secondary distribution. And what you can see there, reading from left to right, so as you increase current from left to right, you'll then hit the first curve, which in this instance is our LV board A LHS incomer. So basically, in this instance, we're going to take off all of that sub-distribution, so both DBA1 and DBA2 will trip and we'll lose power to them. If the fault manages to get past that one, we then hit the red curve, so to HV incomer, and that then takes off the transformer. So now we've pretty much lost power to all of our distribution now. And this is the point that Dan mentioned earlier on, once you start taking power off to the whole of your distribution, or one side of your distribution, you're looking at some serious problems on there. And basically what this is illustrating is that there is no coordination whatsoever. In fact, it's probably going to be luckiest to see whether you actually predict what's going to operate first. So Once we've ascertained that there is no coordination, we then start to adjust our protection settings to achieve that coordination. We then go and produce the TCC curve again. And when I say produce, this is just in software models. This is not, sketching them out or drawing them. We then visually check the curves again. And finally, we get to the point where we've got a coordinated piece of distribution. So now you can see that the curves are in a much neater order. And again, moving from left to right, increasing current. So if we get a fault on DBA1, the first piece of protection that operates is LV circuit breaker 1. And that then just isolates the fault that's beneath DBA1, kills off the power, the rest of the system's operating fine. If, for whatever reason, that piece of that fault propagates above that circuit breaker, it then hits the blue curve, which is the main infeed onto LV board A, and we isolate the whole board. But again, that's as planned, that's what we want to go and do. And finally, if the fault manages to pass through that LV protection device, we then hit the curve for the transformer, which is the red line, and we take off our HV circuit breaker and isolate the transformer. But again, that's as it should be, that's how it should be designed to do. Remember, Dan illustrated those numbers on our electrical drawing. So 1, 2, 3, 4. That's the order you want them to operate in, and that's exactly what we've achieved on there. Just a couple of final points on there. You'll see in the green. These are the transformer characteristics. So you've got the transformer inrush current, you've got the transformer dynamic settings, and you've got the transformer thermal settings as well. You need to keep your eye on them. They're all fixed because the transformer is built the way a transformer is built, but you also need to grade and take those into consideration. So just to summarize, our original settings, we had no coordination between HV and LV. Any fault on DBA1 or A2 would trip the main incomer or the HV transformer. We don't really know. And just as a quick note on there, your transformer protection should be typically in the range of 120 to 130% of your transformer primary full load current. This was at 152%, so you can actually possibly even cook your transformer. Once our proposed settings are implemented, you've improved the coordination, the device is now operating the correct sequence. Transformer feeder protection has been reduced such that we're now at 124% overload. And really, the result now is that any faults on either of those LV circuits, DBA1 or A2, would now trip the relevant LV protection. Just one point about the fuse that's on there, that fuse switch, because they're difficult to grade, they're a fixed piece of equipment, and that's the reason why the curve is generally a straight line. Very difficult to grade with large fuses, and the issue is here is, the only way you can get it to coordinate is you reduce the size of your fuse. However, you reduce the size of your fuse, what in essence you're doing is you're downgrading your distribution beneath that. So you, for example, had a 1000 amp fuse, you've got a typical load of 900 amps, and you have to go down to say 500 amps. You're losing a lot of power from there. So it's something that you need to consider with fused protection. So we can go back to our drawing again, and you can see from on the HV circuit breakers, this is this 120 to 130%. Those were originally at 85 amps. We've reduced them down now to 65 amps to help with the grading. Our main LV circuit breaker for circuit breaker 1, that's come down to 800 amps from DBA1, so we now reduce that one. But remember, I've also mentioned about that fuse, that's at 1000 amps. It's not particularly grading very well, but again, it needs to be one of those assessments where you have to consider what your board load is before you start looking at that. So finally on this, you can see on LV board A where the specifications are. So we've got a board that's rated at 630 amps, and in red you can see the short circuit rating for the board is 25K at 3 seconds withstand. While doing our coordination study, we've determined that the fault levels for that particular board are at 25.53K, and these actually exceed that switchboard fault rating. And what the consequences of that, as the picture showed earlier, if that level of fault contribution is put onto that board, you can run the risk of damaging that board permanently.
And one final thing just to consider on that as well is in your design is how you plan to operate your board. So in this instance, from a reliability perspective, the likelihood is that you've got transformer TX1 and TX2 feeding LV board A, LV board B with this buzz coupler open. A lot of systems are set up like this, so you've got resilience or N+1 as an arrangement, so that in the event that you need to maintain a transformer, maintain a circuit breaker, if you have a fault, that you can buzz couple that board and power the full LV board A and B through one transformer. This is quite a common approach. What obviously in this example, the design has been quite poor, with the short circuit current being 25,000 amps, 25 kA for this section of the board. And this section of the board, one of the considerations is how you operate this buzz coupler, what your operational control measures are. So a lot of switchboards like this take this into design account, and what they'll do is they'll fit mechanical interlocks, such like Castell keys as an example, where you have to physically open this circuit breaker in order to remove a Castell key or initiate a mechanical interlock to then allow you to operate this buzz coupler. That being so you don't have nigh on double the fault current on the board at that time when you've got two transformers in parallel. Again, another consideration is whether some people override the Castell keys. It's again of knowing what those fault levels are and just taking that into consideration in your risk assessment approach.
This is just a point here about fault levels. We've got a piece of switchgear there. This is the main protective device on the LV side of the transformer. And there's two labels on there. So we'll look at the bottom label, which you can see just on there, it's red, and you can see there's a danger sign on there. And that's because there's really no protection on that. The only thing that limits the current at that point is the HV circuit breaker. So you're going to end up with possibly more than your secondary full load current at that point before your transformer protection is going to operate. And obviously with that, you're going to get quite significant incident energy levels at that point there. And I know I've drifted off onto incident energy now, but I will bring this back. The top label, which is a yellow one, you'll see that that's after the protective device. Because the protective device had its acceptance in place, which limits the amount of incident energy that can be generated in the event of an arc flash event, that label then is reduced, showing that its PPE category is a lot lower. You know, you can actually operate that piece of switchgear with the appropriate PPE on. But again, fault levels, as we mentioned earlier, can change all of that. If you're in field, if your fault contributions from whether it's your in-feed or the equipment you've got on, you know, you can significantly change how those pieces of equipment are going to operate, are going to behave rather in a fault condition. So just moving now on to arc flash, and fortunately, once you've achieved your data collection from your protection coordination study, it is exactly the same process that we would use for arc flash assessment. And really, once you've got all your information in place, you can use the same model to produce coordination studies, arc flash studies, load studies, and so on and so on and so on.
So, yeah, so this is an important point. I suppose just more of a tip really is from a procurement perspective. Often especially if you're just taking over a network and you haven't got some information there, you often tend to focus on your network resilience and your fault levels. So you'll look at protection coordination and fault levels. Whilst you're doing your procurement exercise, a good bit of advice will be to make sure that the vendor can do arc flash studies as well. And that way, again, you know, it doesn't matter who you use. If you get to the point where you've made sure you've got coordination, in your business continuities in safe order, you know, your fault levels, if there's no changes to make, then you can literally use the same model like Jeremy's just mentioned, and just get them to run the report for instant energy to give you your arc flash analysis. So hopefully that helps somebody. Yeah.
So moving on to arc flash now. Once we've got all the information, we calculate our fault levels, as we just mentioned earlier. And Dan's mentioned about the N+1 transformer redundancy that can present fault level issues when you close bus couplers. We calculate incident energy levels. We then conduct arc flash shock hazard assessment. and we write and issue the report. Once the report's been completed, we can then get labeling completed. So just to give you an idea of what incident energy is, and this is defined in NFPA 70E, the amount of thermal energy impressed on a surface measured in calories per centimetre squared. And from also what's referred to in Arc Flash is working distances. And the working distance is basically how far the technician, the person is from that prospective source of an Arc Flash incident. So incident energy, there's a way of calculating it, which is a software which does, but generally what affects it is the amount of current and the duration of that current. And as you can see from the utility or HV supply coming through that transformer into your distribution, you've then got protection that's limiting the current in terms of when it comes to overload. If you've got a pan that's going to be worked on, you need to understand what your fault levels are. But equally, you need to know what your protective devices are and what settings they're at as well.
Yeah, so just to add to that, obviously the way that energy release is in an arc flash is exponential, as shown on this graph. And as Jeremy's just mentioned there, the three factors that are going to determine how serious an arc flash incident is going to be is that working distance, so how close the worker is to the arc flash. And again, this can have various results by, you know, small margins, closer or further away. The short circuit current, the fault current, the fault energy, and how long it takes to shut the power off. So this is just an example of potential that can be caused with this amount of heat, the amount of energy that comes off in a time period. So 0.1 of a second cable fire, 0.15 a second copper fire. So that's where you start getting that expansion of copper into vapor, into 38,000 times its size, and then 0.2 of a second is hot enough for a steel fire. So that is just to give some context, and then just visually to see what that looks like based on time. There's, you know, that's up to a second. That there's no time to react in that. So although, you know, we try and do as much mitigation as we can, in the event of an arc flash, there's very little you can do in terms of reaction times. So it's really important that we try and mitigate that as best we can.
So with mitigation, you know, we start to look at, ultimately go back through a protection study again, and we look to try and reduce incident energy levels by reducing protection setting, by reducing the amount of fault current or the current that can flow through the device. As I mentioned earlier, you know, once you start to reduce your protection settings, you are then basically derating your equipment. So there is a fine balance. You know, you can reach, you know, significant low levels of incident energy by reducing your protection settings. But what you then have to balance that with is how much power do you actually need from that piece of distribution. So we try and do it where we can bring it down to category 2 and under, typically 8 cows and under, and that tends to satisfy most of our clients. So again, it's similar to the coordination study. We adjust the protection setting to get the lower incident energy levels. We then recalculate through the model, and we reiterate that until we achieve results that fit the best middle ground that you're going to get. So you still maintain as much power as what you possibly can through your distribution, but equally you minimize your incident energy levels and hence your PPE categories. So
there are physical mitigations as well that can be applied in terms of like ERMS systems and arc quenching systems to reduce that time, that exposure, and also sometimes change those protection settings when doing certain operations of the switchgear. We'll probably cover them in another session when we look at like technologies to reduce risk.
Trips, yeah.
Yeah.
Okay. So we then revise reports, get our labeling out. This is typical labels in a bus summary table. So just with this one, you can see from the bus summary table, the bottom one, JM 11 kV switchboard right hand side, we have our bus voltage in the third column, which is 11,000 volts. And then we move across to the right hand side column. You can see that a category 3 PPE has been selected. You've got incident energy values, which is 11.76 calories per centimetre in this instance. You've got a working distance of 914 millimeters, which is about 1 meter, 3 feet. and you've got your arc flash boundary, which is the point where you're down to 1.2 cals at around about 4 meters, so 12 feet. All of that data is reproduced on your arc flash label. So we've got our label number, we've got our identifier, we've got our arc flash boundary figures, we've got our incident energy figures at the top, and then we've got our PPE category, and also descriptions of what typical PPE we would suggest for body protection, head and face, and for hand protection. So this is typical, and I think you're probably better placed for describing this PPE than Dan.
Yeah, just again some examples of having visual indicators. A lot of companies have matrices built together for how you wear your PPE. So and again, it's good to have these labels on your equipment. It's on the equipment that's relevant to. So in this example, GM 11 kV switchboard right hand side. But then again, your higher instant energy levels, you want to try and have that on your substation or your switch room door, and have a visual indication of PPE type to wear for specific tasking. So it's nice and easy to understand what PPE to wear, what level of PPE to wear when you go into the room. I think it's good to have that visual indicator rather than having a calorific value that someone's then got to go away and start trying to work out what PPE is relevant, because they'll probably tend to go straight for the category 4 standard bomb suit, which is, it doesn't allow good dexterity, it's not comfortable for significant periods of time. So yeah, try and build a decent policy around the outputs of what you've got from your studies to make it usable for the end user, the guys in the pointy end, your engineers, your technicians that are going in and out of these compartments. It's got to be workable for them, especially a lot of these places are hot, they're in the middle of nowhere, they're often tucked away in the back of beyond. So it's good to make sure that it's nice and easy for the guys. They don't have to go out that way to select the right PPE. And I think that's kind of everything we were going to cover. So what we've gone through today, hopefully you understand the importance of protection coordination and fault level studies, why we do them and what we're trying to get out of them. A big area that I see is difficulties in trying to interpret the study outputs, so TCCs. So hopefully the way we've talked through it just in a nice straightforward way, in future you can have a look at your own studies, and hopefully they're readable to you now, or at least you can understand some of the data. Additionally, some of the things that come in those studies are the point I try to make with the LV circuit breaker with the 2 labels on there. They often come in quite often as queries with, which one is it? That mitigation on the incoming cables from the generator or from the transformer into the LV side, the incoming side of the breaker. There's not really a lot of mitigation you can do in that other than adding protection in there, which, as Jeremy said, not many of these are protected. So I just want to reiterate the differences between those. So hopefully that's broken down some of those questions that I often get. And then finally, how all those points link in with incident energy in terms of arc flash and what some of those mitigation strategies can be and what the outcomes of those are as well. So as I mentioned, the next part of our journey is going to be looking at electrical failure investigation. So we're going to look at a real incident that occurred on an industrial site, what the impact was, and then how to go through that root cause analysis process. So we're looking to bring people in from a data center environment, renewables, and heavy industry to give us that diverse spread of knowledge, and then try and work through that together to hopefully come to show all of the different things that we should be looking at in the terms of an RCA on an electrical failure. If you do want any more information on this, or if you want to discuss, I suppose, any areas of asset management to do with your electrical distribution network, get in touch. My details are I've got my details, and Coval's details are here as well if you want any further information on fault level studies, arc flash or protection works. And thanks very much. If we've got, we can go to Q&A, Ben, if we've got any in.
Yeah, of course. So the first question is from Jose. So hi, Jose. I hope everything's well. Is this term selective tripping still used to explain this type of coordination. So that was in relation to the hazards and consequences slides.
So over to you, Jeremy.
I think the short answer is yes. Selective tripping by inference means you are selecting to trip particular devices in a certain order. Coordination ultimately achieves that same aim as well. So yeah, I think they probably go hand in hand. There may be some specifics with selective tripping, like you may, have particular reasons where if you use the example of a hospital in medical care where you're not going to go and trip a life support machine, you've got different types of systems on there to maintain power. Those types of terms, selective tripping, may be incorporated where you've got critical, and I mean critical power requirements, but typically coordination, selective tripping, and there's another term as well that escapes me at the moment, tend to mean a similar sort of outcome.
Excellent. Shall I keep going?
Yeah.
So the next question from Ian. Would you expect faults within the fault withstand capability of a board to be contained within the enclosure?
Oof. How old is the board? The short answer to that one's yes. Yes, you'd like to think that the design of the switchgear considers the fault level or withstand within that the steel frame, the steel structure. However, what you pay for is what you get, and typically older pieces of switchgear may not have the knowledge of what we have now when they came to design them. You'd like to think that it would be able to contain it, because ultimately once a fault occurs and it's at a level that's going to destroy the equipment that it's been applied to, that fault would quickly dissipate. So therefore there'd be limited duration. However, the number of times that I've seen switchgear that's just been blown apart suggests otherwise.
It's interesting, isn't it? Because again, in relation to the two parts of the study that we're looking at, well, the three parts, but fault levels. So with like older switchboards, you often they were built quite stout, quite solid. Yeah. So from a fault level in a withstand in the event of a fault, often, not all, but typically they would contain that quite well. They would be able to withstand the fault current long enough for the protective device to trip and then disconnect. Often you would then do afterwards you would do a post-fault maintenance, and typically they were pretty good, weren't they? The older types of switchgear. But from a instant energy perspective, the way the older types of switchgear were designed and laid out, from a arc flash perspective, it was often very, especially for like withdrawable switchgear and stuff like that, the blast route for your instant energy was typically as the shortest route. So typically out the front, there was no whereas a lot of newer boards, they're built in with, arc, like to direct the arc, arc shoots, yeah. So either out the back, out the top, or to one side of the board where it's away from the operators. So I suppose there's two different answers to that, isn't there? Fault level, you'd like to think as long as it's within its design capability, yes. But from an instant energy perspective, it depends on the makeup of the board. If it's older and it's designed just to blast out the front, or if it's a newer type design that's been designed to take into account arc mitigation and divert that away from the operator.
Good stuff. So this next one's from Dave. So how have you found that the DC fault current and coordination is frequently left out? So this was from the time current curve slides.
Yes, is the short answer quite often. AC systems are far more prevalent, but equally as we start to move into battery storage systems, you see those DC issues starting to come through. So I think historically, because DC's never been considered, that's the way things have always been. However, that's not necessarily the right approach. And I think, yes, DC now needs far more consideration, not just for the fact that it's being used in, as I say, battery storage plants, but also there is, the likes of how much DC is available just through conventional power systems. And yeah, I think you're right. It does need to be considered.
Thank you. So this next one's from August. So is the 25KA for 3S withstand the LV boards as the rating stated 630A or the MV board?
So the 630 amps is what the board is rated for. That's its conventional power consumption. So same way as you had a 25 kilowatt motor, it's going to use, consume about 25 kilowatts of power when it's, fully loaded. The difference between the short circuit rating and the board rating are that in the event of a fault, the board will withstand the 25,000 amps for 3 seconds before it disintegrates. The 630 amps is what it's normally rated for its normal operation. That's the difference between those two values.
Thank you, Jeremy. So another question from Dave here. So DC fault current and arc flash seems to get overlooked in studies.
Yes, the DC arc flash is something that our guys here are trying to get their heads around as well. DC arc flash is becoming more prevalent of the requirements for those studies are becoming more prevalent. And it's not something at the moment that we've really entered into. Not a lot of our clients are after DC studies, although I am aware that their requirements are growing.
Yeah, especially with the amount of, like you say, battery storage, bigger UPS. There's a lot to be considered there, isn't there, from a DC side?
Yeah.
There's some good comments and some good shares that I want to talk about, if that's all right. People put in the chat. So this one's from Michael. One best practice is to confirm that all breaker trip settings match the SCCS settings, and then we apply a tamper seal over the breaker setting cover.
Yeah, it's interesting. That's yeah, it's not a bad thing to do. It's yeah, I suppose as long as it doesn't take anything away from investigate, if you had a fault, if you've got to access the relay settings to get through to investigate, your fault log, things like that on the relays. I think as long as it's just the adjustable parts for you, it depends if it's electronic, doesn't it, or electronic and electromechanical. But yeah, it's a really good input. Appreciate that.
This next one, so a comment from Christian. So I saw an incident where the arc flash fault lifted the entire panel, which had not been anchored to the floor, and it fell onto the engineers. They were not injured by the arc flash, but were crushed injuries from the panels themselves.
Installation standards, hopefully improved since those things. But basically, if you're not bolting your panels down to the floor, there's the risk of toppling. And once they, try and terminate a cable on a panel that's not bolted to the floor, it's not the easiest thing. But that's a fairly significant event, that one.
So this next one's from Matt. So biggest issue we had with studies, Navy and unnamed company, was that techs would adjust settings to remove nuisance faults, vice troubleshoot and repair the actual problem, and not update engineer record or asset managers to update drawings, coordination, or arc flash studies.
Nailed it. Absolutely right. So, and basically, these are undocumented modifications, as their collective title is. People adjusting things just to keep the plant running, the equipment running, whatever it is. And I think it's one of those, if you formally report, look, I've got this problem. This is what the answer is. What's the process for getting my answer implemented, rather than just go and do that themselves? Yeah, real big deal, that one.
And then I'll make this the last one then because we're up at time. So this last one's from Jose. An issue I've seen with the SCCS is during confirmation and verification of the settings on the breakers, where the SCCS study called for a certain trip setting, but that adjustable setting was not available on that specific breaker.
Good point. So we've had this as well. Yeah, we've had this as well. And basically it's, you're trying to get your protection devices to do what they're not set up to do. So, when we do our modeling, this is why the collection of data is super important. So if we don't know what the protective device is, or we don't know what the CT ratio of it is.
And we're talking make and model, aren't we? Specifically,
yeah.
you know, that exact type of relay.
Yeah, exactly. We try and model that, and we're not sure. You know, we've got a vague understanding of what the device is. We can end up proposing a setting, and you know, we get to site, and the guys are saying, "Well, this setting isn't even on here." So yeah, you get short circuit current values where you're asking for a particular trip setting, but you cannot achieve that because the range isn't available on the protective device. And that pretty much boils down to when the study was implemented, the information that's being taken away from site has been incorrect.
Yeah.
And then the last thing from my side, just that the survey will be coming out in about 5-10 minutes after this session finishes. If you could please spend a minute to complete it, let us know how we did, where we can improve. If anyone would like auto-registering for future webinars like this, please feel free to drop us a message. And for all those that did mention to get the previous recordings, I'll get them sent across this week.
Thank you, everybody.
No, thanks very much.